So good morning, students, again. Good morning. We're going to get ourselves going. It's a cool day today because of the weather conditions. So, anyways, we will continue. So, yesterday afternoon, we left off working with that method of mixtures. So, we're going to look at an example where that is concerned. All right, so let us get going. All right, so we're still, listen up students, we're still on specific heat capacity. All right? That's our main topic. But we're going to look at an example of how we can use the method of mixtures to find the specific heat capacity of a substance. So we're going to put an example here. So we're going to say that, let's say that an unknown metal of mass, let's say the mass is, let's make it a little easy, Akila. Let's say 100 grams is, 100 grams at also 100 degrees Celsius is placed in a styrofoam cup with if I don't hear you. Yes. And I'm going to tell you why I specify, right? With styrofoam cup, with water, with, let's say, with 125 grams of water at, let's say, 28 degrees Celsius. 28 degrees Celsius. After a short while, students listen up again. Should be taking note of the example. You can continue, yes. You can continue. But maybe put the date so that when you're checking back, you can know that, okay, on the 25th, we'll look at this. Okay? After a short time, the mixture, after the temperature of the mixture was, let's say it was probably 35.8 degrees Celsius. All right? Now we're going to say that all right, let me not put it in the question. We're going to now say, calculate something. So calculate the specific heat capacity of the metal. All right? So this is our scenario that we're working with. So we have this metal. So let me give you a little while to take that down first, and then we can start discussing. Huh? Yeah, this is based on what we looked at yesterday in terms of the method of mixtures. All right? So we're going to consider the method of mixtures here. Yes? After a short time, the temperature, yes. The temperature of the mixture was at 35.8 degrees Celsius. And we want to know the specific heat capacity. So for this, we're going to consider the method of mixtures, right? Why the method of mixtures? Because we have two substances that are going to be combining. We're going to combine the metal with the water in the styrofoam cup. And just to note that the specific heat capacity of water, what's the value? 4,000? 4,000? 200, right? 4,200 joule per kilogram per Kelvin. Okay? So we're going to need that. Right? So again, this is our scenario. And we're saying that we're using a styrofoam cup. Now, the reason why we use a styrofoam cup is because the styrofoam cup, it has negligible heat capacity. Right? It has negligible heat capacity, so we're assuming that no heat will be transferred to the cup. Right? So the heat exchange is going to be just between the metal and the water. Right? So we can ignore whatever heat or that will be transferred to the cup because again, because of its heat capacity being negligible, there's no heat that's going to be transferred to the styrofoam cup. So essentially, the styrofoam cup is acting as an insulator. And we're going to need that because we could have heat actually be transferred to the environment. But the styrofoam cup is actually preventing that. So as you are thinking about your experiment, students, these are some possible sources of error, right? Heat, you're losing heat to the surroundings. So when you're doing the experiment, we're going to use a styrofoam cup as a means of providing that insulation. The ideal thing to use is what we call a calorimeter. The ideal thing to use is a calorimeter, which is just a can that has some insulation, right? Maybe when we're going to do the lab, I can probably show you an image of one, or you guys can Google it, right? A calorimeter. Anyways, so we have this right here, and we want to find the specific heat capacity of the metal. Now, notice it says that after a while, when the metal was in contact with the water, both of them reach this temperature, because it says that they were, the mixture was this, so it means that the two substances were now at equilibrium, right? So this is our equilibrium temperature, so it means that the metal is at 35.8, and the water is also at 35.8. So since they are the same temperature, no heat exchange will occur, okay? So we're going to now use that information now to help us to solve the question. And again, because both mixtures are at this temperature, remember that the metal was at 100, it went down to this, so it would have lost heat, right? The water was at this, it went up to that, so it would have gained heat, right? So we can now make a statement that I'm going to say heat transferred, kind of shorthand today, is equal to the heat that is what? Heat that is what? No man, heat transferred is equal to heat gain, right? Heat gain, right? So that's our assumption. And again, we can assume that because we have the styrofoam cup and no heat is transferred to the cup or to the environment or vice versa. Okay? So there's no heat exchange between the cup and the contents, nor the environment and the contents. So we can make this assumption. Okay? All right, so with that being said, now we can write that MC, and again this is for the metal, delta T for the metal is equal to M for the water, C, water, delta T for the water. So that's our expression, right? As we did yesterday, we divide through by M for the metal, delta T for the metal. And when we do that, we're going to get that C for the metal is equal to M for the water, C for the water, delta T for the water, divided by M for the metal, delta T for the metal. So that's our statement here. Okay? Yes, because we're talking for the water. Yes, yes. All right? So let's work out, because we have the mass, we know the specific heat capacity of water, and so on. So let's do this. Now, yesterday, when we were talking about conversion, I would have stated to you that, okay, we can have situations where we will not necessarily have to convert because the units, they're going to cancel out. And this is an example where that is the case. So we could go ahead and actually work with the mass in grams, right? Because the grams are going to cancel out, right? So let's find the change in temperature of the metal and the water, okay? So we're going to say delta T for the water. It was at 28, then it went to 35. So we're going to subtract the smaller one from the larger one. So we're going to have 35.8 degrees Celsius minus 28 degrees Celsius. That's what? 7.8? Like that? 7.8 degrees Celsius. And then let's do delta T for the metal now. So delta T for the metal, it was at 100 degrees Celsius. It went down to 35.8. So 35.8 degrees Celsius. That's what? 64 point something? 2? Yeah. So 64.2 degrees Celsius. So now, what to do now is just simply plug in and simplify, right? Or evaluate. So C for the metal then now is going to be M for the metal. We're going to use the mass in grams because, again, the grams are going to cancel out. And you're going to see it. So the water was this. So 125 grams. Specific heat capacity of the water is 4,200. So 4,200 joule per kilogram per Kelvin. Yeah, we're going to see it. Because we're going to have gram in the denominator as well for the mass of the metal. So they will cancel out, okay? And delta T for this now was 7.8 degrees Celsius. Or we could say 7.8 Kelvin. But again, the degrees Celsius will actually cancel out as well. All right? Yes, they always have to reach equilibrium. Right? Always. Okay? So you have to remember that, okay, once they're equilibrium, both substances will have that final temperature. Okay? Yes. What does the M, wait, that little M, okay, means for the metal. Metal, and W is for the water. Okay? So for the metal now, the mass of the metal we say was 100 grams. So we have 100 grams right here. And the change in temperature was 64.2. So 64.2 degrees Celsius. So again, notice G cancels G right there. That cancels that. Right? So the only unit we have left is this. Right? So our answer is going to be in joule per kilogram per Kelvin. Right? So in this case, as I said, the units cancel off. So since we're aware of that, we did not necessarily have to convert. But if you're not certain, the best thing to do is to convert because you can never go wrong once you're working with SI units. Right? So if you are using your calculator now, you're going to be able to determine the value for this. Wait. Initial, right? Exactly. Yes. We always say this, subtract the smaller from the larger, always. Yes, we make an error? Okay, good. All right, so plug that into your calculator for me and tell me what you get. How much? 637? 637.5, so let's say about 637. So let's say about 640, right? Round it to 640 joule per kilogram per Kelvin. So that's the specific heat capacity of the metal, right? Yes. Yes. Okay. Another ticket? So work the top first. So use brackets. So if you know, use a bracket here, so, and a bracket here, so, right, to be safe. Right? And you get something different? What you get? Yeah, man, but we're round, yeah, same thing. Because we're round to 2 sig fig. Right? We're round to 2 sig fig. Right? Round it to 2 sig fig. No, it's not wrong. All right, so remember, the reason why I round it is because I want us to now do a Google search. Yeah, we wanted a whole number, 1, and because of the numbers that we're actually working with. So I just round the 2 significant figures. Right? But what we're going to do next, you can write the decimal and then write this as your final answer. Okay? No. No. Okay? Yes. So, now that we find the specific heat capacity, remember I said that we can identify a metal by its, or an object in general, by its specific heat capacity. So, let's say if we can do a Google search to say, okay, which metal or which object, because I don't know if it's a metal, which object has a specific heat capacity of 640? Yeah, we say a metal, but I'm saying, I'm not sure. Maybe it's something different, I want to know. But let's try to say if there's a metal or some other object that has a specific heat capacity of 640 joule per kilogram per Kelvin. Yes, so Google it. Google. Which substance has a specific heat capacity of this? Okay? Anybody found the object? Or something close to it? If we get something close to it, we can work with it. Anybody? We want to know which substance has a specific heat capacity of that. We're trying to see which substance has the specific heat capacity. Okay, so calcium, okay. Okay, so maybe the substance right here would be calcium metal. Right? So students who are talking, so we found, so the closest one we found was what? Calcium, which has a specific heat capacity of? 631. Right? So, it's a possibility that this could be, the metal in question could be calcium metal. Right? No, on the lab. No, exactly. But if I'm asking you the question, I'm going to give you information. Maybe I'll give you a table with some specific heat capacity, and then based on your results, now you should be able to match it up. Right? You get aluminum, what you get for aluminum? What's the value for the specific heat capacity? Huh? Okay. Right? So that's that. And again, for your lab, you're going to have a situation like this where you have to state what the metal is, and you might have to do some Google searching. All right, so that's that. So we're going to look at one more method now. So we're going to look at the method of electrical method. Electrical method. All right, so the electrical method. All right? So let me sketch the diagram first. All right. All right, students, stop talking. 628. All right, so even though we get 628, Shanoya, there could be probably some errors in the experiment, right? Why we don't get the exact value. So that's also useful now when you do the lab, right? Because maybe when you do the lab, you don't get the exact value, but you get something close, you can talk, say, okay, maybe some heat was lost to the surroundings as a source of error. All right, so we're going to do this one now. Sorry. Huh? But it's a device. Yeah, a meter. A meter. Here? Yes. With a A inside and a circle right here with a V inside. Okay? So this is our diagram. So this right here is what we call a lagging. And you should remember this term lagging from when we were talking about yes. When we were talking about Joule experiment, right? And it was surrounded by a lagging. Right. So this right here is our metal. Right? And this is our heating element. Right? Heating element. This right here is our thermometer. Okay, so you guys can copy down this diagram. Now that we have gotten the opportunity to draw down the diagram or copy down the diagram in our notes, we're going to just outline the procedure. Now, in terms of carrying out the electrical method, there are some initial setup steps that are going to be required. Because we're going to have the metal right here. And I probably should make you see the metal because, you know, like an outline for the metal, what do you think? Right? Because it just look like it's just a lagging. Right? So let me just do that. Let me try if I have another color like black. Yeah. So, I don't like it. But anyways, I don't like it. Anyways, the metal is going to be inside. Right? And it's going to be surrounded by the lagging. Now, what we're going to do is we're going to actually drill some holes in the metal. So we're going to drill one hole for the heating element, and we're going to have another hole for the thermometer. Okay? Because we're going to need to monitor the temperature of the metal as we are supplying heat. Right? Yeah, so it's going to be in the metal, and we're going to have the lagging around it. Okay? So it's metal we're going to drill. Okay? All right, so let's look at the procedure then. So the first thing we're going to do, after we would have done our initial setup, is we're going to measure the mass and initial temperature of the metal. Temperature of the metal. Right, so we're going to do that first. So again, this is going to be a summarized version because I don't want you really necessarily to write out a long procedure because on the exam, if you're asked to describe, you should be able to describe, generally, right? The key aspects. So we do that. Number 2, we're going to close the switch. The switch for SWITCH for, let's say, about 5 minutes. 5 minutes. right? Then we're going to record the new temperature of the metal, right? And 4, we're going to record the reading on the ammeter and volt all right? And then 5 now we're going to say record all results. All right, so record all results in a suitable format. All right? So that's our procedure. All right? We need to know the initial mass and initial temperature. We're going to close the switch for a few minutes, as I said, about 5 minutes. Allow the heating element to heat up the metal, right? And then we're going to record the new temperature of the metal, and then we're going to also record the reading on the ammeter as well as the voltmeter. And then we're going to put our results in a suitable format. So maybe we can list them down or we can write a table. And we're going to consider the similar situation that the element is transferring heat to the metal. Okay? So we're going to look at that in a minute. All right, so that's the procedure. So again, I summarize it. So, you know, when you're looking it over, I mean, if you are asked to reproduce it on a paper, you have the summarized version so you can describe it. Okay, so we're going to consider that, yes, the heat transferred by the element is going to be equal to whatever heat is gained by the metal. So we can say heat transferred is equal to heat gain. Right? So heat transferred is equal to heat gain. Now, we have to just, still all right up here, sir? Okay. I will give a few more minutes then. All right, let's go now. So, we say that heat transferred is equal to the heat gained. Now again, remember students that we have an electrical heater, right? So we have to consider now, okay, how much energy this heater is going to actually supply. Now, there's an equation, right, that we want to be aware of. And I'm going to put it right here. So the equation is that electrical power P is equal to I times V. So watch me, guys. Electrical power P, students? Yes, sir. Yes. Electrical power P is equal to the current multiplied by the voltage. So P is equal to I times V. Okay? Now remember that P is also equal to E over T. So what it means then is that we can equate both. Warburton, we can equate both. So since this is P is equal to IV, this P is also equal to IV, we can write that IV is equal to E over T. Right? And again, we want to find what? Energy, right? Heat energy. So we're going to make E the subject, multiply both sides by T. Right. E is energy. So we get E is equal to I like to write it as this. I V T. Right? I V T. Right? So the energy supplied is going to be given by I V T. Right? I V T. Right? So I'm going to let that stay right there. It's going to be on the board. So you get time to take it down. So, watch me, students. The heat transferred is going to be given by IVT. Question? Heat transfer is going to be given by IVT. So we can say then that IVT is equal to MC delta T. Students, guys, you have to pay attention, you know. Please, pay attention. So we're saying that the power, electrical power is equal to I times V, which is current times voltage. But power also now is equal to energy transfer divided by time. So since we have two expressions for power, we just equate them. So we get IV, which is power, is equal to E over T, which is also power. Okay? And then we just make E the subject, and we get E is equal to IVT. So the energy transferred by the heating element, electrical heater, is going to be given by the current flowing through it, multiplied by the potential difference, or the voltage multiplied by for how long it was operating. You're going to see it in chemistry in terms of electrolysis. Right. Right? Good. So, we're trying to find C. So, we just divide both sides by M delta T. So, C then now, students, is going to equal to I VT, which is the energy, divided by M delta T. Okay? So, that's how we can use the electrical method to find the specific heat capacity of a metal. Okay? Yeah, that's the final thing. If anybody doesn't follow, let me know. I is the current that we're going to get from the ammeter. And V is the voltage that we get from the voltmeter. That is why we have to record them. Yeah. Huh? Something similar, but the IVT is first time we do it. Right? First time we do it. T is time, yes. Right, so we're back in session now, so let's go again. All right, so we're going to look at an example related to this. I'm going to keep the diagram here because I want to maybe reference it when I'm going through. So we're going to say over here. All right, so we're going to say that an experiment, yes, please. Huh? Yes, you can go. An experiment was conducted. Yes, example. Right? Conducted to determine the SHC. What does SHC stand for? Right? Of, all right guys, quiet down again. Of a metal using the electrical method. The results below were obtained. Okay, so let's go. All right, so we're going to say that T is equal to 5 minutes. I is going to equal to 0.5 ampere. V is going to be 12 volts. Right? And let's say that M, do it over here, M is going to equal to mass of the metal let's say 5 kilogram, right? And T1 is going to be maybe 24 degrees Celsius. Let's see that now. 300 times that. 150. 380. T2 is 60 degrees Celsius. So that's what we have, right? That's what we have. Right? So that's what we have. So we have our information, right, like that, and we want to calculate. Somebody said calculate a while ago? Yes, good. The specific heat capacity of the metal. All right? So again, we're going to start off by stating that heat energy transferred is equal to heat energy gain. All right? And since it's electrical, we can write IVT over there, so IVT is equal to MC delta T. And we know that C is going to equal to IVT over M delta T. So we know that. Now, let's look at delta T. So delta T is going to be this right here. So delta T is going to be 60 minus 24, which is 36, right? 36 degrees Celsius. So we have all of that now. We can plug in right here. So this now becomes, I would say was 0.5, so 0.5 amperes times V, which is 12 volts, and T is 5 minutes. But again, remember we have to express it in seconds. Right? So this becomes 5 times 60, which is 300 seconds. So we have 300 right here. And then we divide by M, which is 4 times, well, let me use the units, kilogram, times 36. Right? And I'm going to say Kelvin. A 5, yeah, good. 5, yes. When I was thinking 4, but then I decided 5, so I guess I was like locked in with the 4, yeah. Good. So, see then now. Okay? So we're going to have that, and let's do the maths. So that's 1800. 1800 divided by 108. So that's what? So 100 and something? I don't know, I just work with Renee. I remember what I said. I just repeat what I said. 10%? Okay, so it's 10? Confirm? 10? 10, okay. So we get 10 joule per kilogram per Kelvin, right? This? Not next to a meaning. Without the units? Mm-hmm. Oh, okay. But this is really energy, you know. All this right here is energy in joule. Yes, you get joule per kilogram Kelvin. Okay? So students, notice that we have ampere, volt, and seconds. But remember we said that, okay, when we multiply ampere, or current, voltage and time, we get energy. So all this right here is just joule, right? That is why we get joule per kilogram per Kelvin, okay? So we get 10 in this case. So it's an example, all right? It's an example. Now, being that this value is so low for the specific heat capacity, it means then that the object in question is a superconductor, right? But again, for the sake of the example, we get this value, but realistically, you will get values like 200 and within that margin. But again, for the sake of the process, we got that right there. Okay? That's your hand. Savannah, you were raising your hand? Okay. We have any, what time? What time is it? A time or no? 22 minutes? All right. So I'm going to give you a question to attempt in 20 minutes. All right, so guys can take down this right here. I'm going to send an example for you to work on. All right? So let's take your time, take it down. I'm going to send one related to this so that you can apply the same principles.